Hi, my name is Michael Selzer and I'm a senior here at Vanderbilt University where I'm studying electrical engineering, which relates very closely to the lesson we're going to do today, which is electromagnetism. At Vanderbilt, in my free time, I'm also involved in research and also Vanderbilt Motorsports outside of my main commitment, which is VSVS, and I'm excited to teach you guys today.
Hi, my name is David Ward. I'm a senior at Vanderbilt University, majoring in computer science. And outside of VSVS, I'm also very involved with Vanderbilt Off-Broadway. And here's our lesson. First, let's think about what we already know about magnets. All magnets have two magnetic poles, a north pole and a south pole. For a bar magnet, these are at the ends of the magnet. The poles are the places where the magnetism is strongest. The same poles repel each other. See, if I put a north and a north together, they really don't want to be together. The same is for two south poles. Two south poles also repel each other. But opposite poles attract. If we put the north pole of one magnet close to the south pole of another magnet, they will attract each other. An electromagnet is made by wrapping copper into a coil. It generates a magnetic field when an electric current is passed through the wire.
Hi guys, so now we get to experiment with electromagnets. So right now, out in front of me, I have two different electromagnets, and they are made by wrapping a copper coil around a nail. As you see, this one is wrapped around 10 times, and this one is wrapped around 50 times. Let's experiment with their properties. So let's test what happens when we touch these unelectrified electromagnets to the paper clips. Neither electromagnet picks up any paper clips. Okay, so now we're going to get to experiment with electromagnets. As you see here, I have the electromagnet that has the coil wrapped around 10 times, and then you will create the circuit that you see here with the batteries and a push button switch, which is currently off. So I want to turn it on and complete the circuit and run some current through this electromagnet. So let's see what happens and how many paper clips I can pick up when I do that. We got some stubborn paper clips here. Okay, so now as you see, I have the electromagnet that has the coil wrapped around 50 times, and I wonder how this is going to affect the strength of the electromagnet. Again, I can do the same thing I did last time, press the switch, see how many I can pick up. Whoa. So first let's see what a permanent magnet does when touched to the paper clips. And here we have a magnet. It is not connected to any wires. We touch it, and it picks up all of the paper clips super easily, and they're stuck on there pretty well. And now you will create this circuit with the snap button kit that you have, and you can see that we have a slightly different electromagnet. And how do these coils compare to the coils in the other electromagnets? As you can see, this one has a lot more coils than we had before, even in the 50 turn coil. Okay, and now we're going to try a similar experiment with a different electromagnet. So the button is not pressed. Let's see how many paper clips I can pick up. Not many. Now I will press the button. Oh, and I have much better luck now. Even more than we could before with the 50 turn coil. And now I will let go of the button. So can you guys think of a real-life use of that technology? As you saw, when I released the button, all the paper clips fell. And this technology is actually used every day in junkyards all over the world. Think about it. You have a really big electromagnet that could pick up cars and other old metal pieces of machinery. And you could pick them up and bring them somewhere else, then release the button, and then they will just drop. This is super useful and used all the time.
Now we're going to see what happens when we combine two magnetic fields. So first you're going to take this piece of equipment that you were given. You're going to make sure that you put a battery in the bottom of it. And then you're going to put this little ring here on these two holders and spin it with your finger and watch what happens. Why does this work? Let me explain. So, by putting the battery in the bottom, these two copper pieces here are connected to that battery, and then when they touch this wire, they make a magnetic field, right? Just as we've shown with the nail previously. But actually, the circuit's not always being completed because on one of the ends of this wire, there's some coating that's scratched off, meaning that when this part touches this copper part, the circuit will not be completed and will turn off. So what's happening is, when you start spinning it, right, when the working part of the wire is connected to this copper, it's completing the circuit and making the magnetic field here, which is repelling the magnetic field of this permanent magnet here and making it spin, right? But then part of every rotation, the uncoated part of the wire is connected here, which is turning the circuit off, basically, right? It's the equivalent of letting go of the switch. And the magnetic field from the wire is stopping, but the momentum from the wire keeps it spinning, and then it keeps it spinning until the circuit is completed again. And so it just continuously connects and disconnects the circuit, creating spinning that can go on forever. Whoa! Check that out.
So far throughout the lesson, we have used electromagnets and batteries to create a magnetic field. And what we have done is we have used electricity to create a magnetic field. And we needed batteries for that. But with electromagnets, we could actually go the other way. We could use a magnetic field to then create electricity. No batteries needed. So how do we do that? Well, something like this, which is a little generator. So what we have here is a little LED light, which will light up when there has electricity running through it. And as you see, there's no batteries here at all. All it is a copper wire, as we used before, and then a magnet inside. And when I spin it really fast, the light lights up for a little bit. If I spin it slowly, it doesn't quite produce enough current to make it really bright. But again, I do it fast and it gets pretty bright. And if this was able to spin continuously, the light would stay on. So let's talk about some real life applications of this. So we found that as long as we could get something to spin, we could create electricity. So maybe we could create some renewable energy source, and as long as you have something that spins, you get the electricity from that and either put it into a battery or add it to the electric grid. Can you think of something that uses this type of technology? For example, windmills do this exactly. They use the wind and some great engineered aerodynamics for the blades, and they spin those blades continuously. Whenever there's wind, they're going to be spinning, and they're going to be lighting the LED, they're going to be powering homes, and stuff like that. Another example would be a hydroelectric dam. It uses the power of the water flowing downhill to spin a turbine, which then creates electricity, just like this generator here, but on a much bigger scale.
We hope you learned a lot about electromagnetism today with us. See you at the next lesson.